Okay, so this is our, everybody can see this? You can see it online?
Yes.
The people online? So if you don't see it, just let me know. And this is an implementation of our agent, of our, environment. And this is a bandit, a K-bandit. And for those who are not familiar, this is what object-oriented coding looks like in Python. So we're going to write a class bandit, and let's get the initialization. This initializes the object. And we have a step function. And so in reinforcement learning, the normal environment has a step function. And the step function, you tell him an action, and it will return you like the reward and the next step, and and some other information you need. And we say, okay, we can initialize the bandit. We can give it a k. Like a default bandit would look like this, which is like tuples of numbers. Like this is the probability, and this is the reward. So we say, okay, with 50% probability, if you select this arm, you're going to get 1. And with 10% probability, you get this one. And this is like a list. So you can extend it with as many tuples as you want. You can put like 500 tuples, and then you have like 500 arms. And then we say, okay, say self k is k. And then you say self.actions, that's the number of actions we have, is like the range of len k. So the action is going to be a list of numbers, like 0, 1, 2, 3, right? And then later we're going to choose from that list randomly, or based on our policy, we're going to choose from that list. And step is to say, okay, my win probability and score is the arm I have selected. And I say, okay, random choice from that arm. And we take one, so either you win nothing or you win the score, the reward. We make one pool, and the win probability and lose probabilities are just like 1 minus win p is my lose probability, and win p is my win probability. Oops, how's that going? So for those, it looks better in your notebook. You can look at the theory, what this looks like, and this is the epsilon greedy algorithm. And we have one, if you look at the pseudocode, we have like a q, and we have an n. This is the q, and this is n, and this is the self q and the self n. And we have a self.epsilon, which is the epsilon, here, this epsilon.
What is n?
N is like how many times did I visit the state. And q is kind of the q function, the q value function, the value function of the action. And so for those.
So there is a question from online that asks, can you explain what q is in that equation that you showed?
So q is the value function of the action value function. So it basically tells you what is your expected return on that action. So what we calculated before, this is q, where we had the slide with all the equations.
The one that Omar asked?
Yeah, the one Omar asked. And I want to take you some time looking at the code. And who thinks he can complete this function? Like we have a select action, and you just have to complete that function. It's kind of a bit like a Mad Libs for coding. So we can work on it for a few minutes, everybody. You can ask your TA if you have some questions. So everybody.
So let the online people know that you're starting.
Okay, so for those people online, we're going to start coding. I'm going to code the solution. You had your time? So we say something like self.epsilon, right? So if you look at the algorithm, it says we draw epsilon, and we have an epsilon, we draw a random number, and the random number is larger than epsilon. We do the greedy action, and else we do the random action. So we say self.epsilon, and now we have to draw a random number. And this is like left as a hint there. This is how you can draw a random number. Can you see the number, the code? Or it's too small.
But no, we were commenting on our ability to not see it at that time.
And we say, okay, we return self.run the action. And else we return self.greedy action. So that's it. And here, this is how we do a random action. So we do a greedy action. And now I'm going to say, okay, just take the best action, right? So we say so what is this doing? So let me finish typing it and I'm going to explain it. So we select here, we select the maximum of this whole array, the Q array. And then we say, okay, which positions in the MP where returns your index. And we say, okay, where is the array Q equal to the max value of the Q array? So it's going to return you all the positions in the array where you have the max Q value. And then we say, sometimes it can return you multiple positions. So just say, we just select random. We break ties randomly. We just select, okay, we take the first one.
If every time you take the first one, wouldn't that be the best way to do it? Like, would that make it?
Well, you can also say randomly choose anyone, but you can select the first one.
Isn't this the same concept as np.argmax?
Yeah, that's all. Oh, that's all.
np.max?
Argmax.
NumPy argmax function.
Gives you the maximum, the argument.
Okay. Okay.
I use np.argmax. Yeah.
Oh yeah, no, sorry. I have it wrong. So 0, I get the array of all the actions, right? So it returns me all these things where the maximum value is. And then we say the np where. And then we say, we just do a random choice of those np random choice returns me one of those random maximum actions. And now we have to write our update rule. Let's see if we can. So what was our update rule, right? Actions. So let's see if I find. It's 1 divided by self.n action, right? So we divide it by 1 times n times reward minus self.q action. So, and the other things is like, so train, we give it over. This is like a training function. You give it an environment. Here it expects a K-bandit environment, and then it just like say if you want to train, right, and you want to train it more, like you train it 100 epochs, you want to train it more, then you can say, okay, first init is like false. So if self q is already initialized, I can train it, and then I can train it even more. But if I say, okay, I want to clear out self q, initialize self q, you can say first init is true, and it's always going to initialize a new self q.
Just, I'm sorry, I'm going to go back to the update. Isn't it n minus 1 or is it n?
N. It's 1 divided by self.
Actually minus 1 because am I updating the same position? I'll be looking at the action, the previous action.
Good question. Where do I have the code? Well, I just took the update rule as it is here. So the update rule is, like I selected A, right? I have the reward. So if you have it the other way around, it's going to be 0, right? You're going to divide by 0.
But won't NA be updated in the phase because
Yeah,
NA comes to the group.
You updated.
It's already updated.
Action
right?
first. Okay.
Okay, let's run this. Fingers crossed. Let's run this. Sorry, I have to run this as well. So now we have we initialize a bandit object. There's like a bandit environment, and then we initialize our greedy, and then we train the greedy one. And then we're gonna do 100,000 now. Let's do 10,000. Okay, bandit object has no step. Oh. That's a big B. So you see it very neatly approximated. Like we have a 0.5 expected return. So you have like get 1 point at 50% of the chance. And in one we have around 10, where you say, okay, 1 in 10 games you get 100 reward. So it approximated the expected return for this action very neatly. So the expected return is like probability times the reward, because it's a Bernoulli process. Bernoulli process is just like you flipping a coin, or like either it's A or it's B. So that concludes our greedy algorithm. Are there any questions for this?
I was trying to debug the last one. It's running it's saying A must be greater than 0 unless no samples are taken. Like, I don't know if it's
we're gonna share the notebook of solutions. So if it doesn't work in your notebook, just something is like a mess. We're gonna yes.
From 10,000, all you need to do try 280 ended up in Harvard 1.
What?
I mean, what does the first bracket mean? Means that from 10,000 down?
So it means 280 times you select this. 280 times you select the first level, and 9,720 times you select the second level. So this is N, and this is Q. People ask what for the people online. So the first here, these two values, these are the N values. So we selected the first level 280 times, and we selected the second level 9,720 times. So this is the N array, and this one is the Q array. Yes.
And this is the
reward. But here, I think we can run it and say 100. It should already give like a good estimate. So you run it 10 times, you see it's like kind of random, right? It's kind of off. So we say we run 1,000 times, is already good enough. It's like, you see it's like roughly 10% away. 10% off.
This is better, so I should go with somewhere else.
Yes. Yeah. No, the next session is going to be more theory. So for people online and for everybody here, we're going to move to theory, but we're going to take a We're gonna take a 5-minute break. Everybody?
So the break is over. We're starting.
So, anyone got any questions now for the code? Some pointed out there's an error in the, not an error in the implementation, but like a kind of a switch around. So I got this like argmax, the greedy at 1 minus epsilon and the random at epsilon. I have it switch around. So I select so like one was like 1 minus epsilon, and have it switch around. So basically I select the, so I didn't have 1 minus epsilon, but I selected only epsilon. But in the end, it's the.
But because you're choosing between 0, 1,
Yeah.
the only boundary becomes the issue. Exactly.
Yeah.
Cutoff.
Yeah. No, it's correct. The code in the one I don't have the 1 minus epsilon, but the code I select an epsilon, and it just even had me just confused.
But you don't need 1 minus, right?
No, we don't need 1 minus epsilon. It's just in the code with probability of epsilon, we select a random action, and with 1 minus epsilon, we select the greedy action. That's